Okay, here we go. So that's a homework, sorry. Let's talk about growth and decay models for exponents. So typically that formula f of t equals a sub 0 times e raised to the kt power will be used for exponential growth and decay models. Now you might remember something like this from algebra 2, where r represents the percent growth or percent decay. And of course, if your base is bigger than 1, that's growth. If your base is less than 1, it's decay. The thing with e is that by using e instead of like these two, you have kind of just one model that you could just focus on. And then k would change depending on whether it's growth or decay. Like if k is positive, it's growth. If k is negative, it's decay. That's why sometimes people use e, because sometimes it's easier to model things that way. It makes it easier for computer systems to run these models instead of like trying to figure out, do I use 1 plus r, 1 minus r? It could be kind of confusing. So we'll use this formula instead. With e, and a sub 0 is your initial amount. K is just some constant that depends on how things are growing, if it's growing fast or slow, or decaying fast or slow, that will impact k. And then t is time. And usually time can be whatever you want it to be. It could be minutes, seconds, hours, whatever makes sense for the model you're dealing with. And of course, a, or f of t, is the amount you have after a certain period of time. Like it could be used for population, it could be used for money, it could be used for bacteria cells, or I don't know, I'm trying to think of other examples, people getting sick, stuff like that. So let's try it. In 1960, the US population was that many people. By 1980, it grown to that many people. Let's build a model for this. Here's what you do. We'll say, I'll write it like this actually. Why think I'm using the letter P? What do you think P stands for? No, in this case, context, guys. Population. Honestly, I don't care what letter you use. You can use any letter you want. I'm just using P. Yes, you're right. I mean, like usually for money, we do a principal. So maybe I threw you for a loop in that one. But yeah, just population, right? So what was the initial population? 0.7. And I'll let P equal the population in millions. So I don't want to put all the zeros because that's kind of a pain. So we'll assume that we're doing this in terms of millions. Do I know K? No. How many years is passing by? From 60 to 80? 20. And what's the population after 20 years? Right. And now all you have to do is use a calculator, which I foolishly left in my other classroom, but that's okay. I'll pull up one here. Probably better that way anyway. Okay, here we go. So 226.5 divided by 180.7. So you get 1.253 equals E20K. And 20K equals natural log. So you got to be very comfortable with the logs by now. If you're having trouble transforming from exponential form to log form, let me know. I'll help you out. But the base of your the base of your power was E. E now becomes the base of the log, and the input now becomes 1.253. The output is 20K. So K will be the natural log of 1.253 divided by 20. Now, one thing I want to caution you about is don't try to round the answer too soon in the middle of the problem, because then you might get a K value that's not quite accurate. So obviously, I just grabbed the K value as it was. Sorry, 1.253 as it was, and got K a little more accurately. So K, I get 0.0113. Now, if you did natural log of say 1.25 divided by 20, I mean, it's not too far off. But you can see it's a little bit off, right? So it's good to be as accurate as you can be, especially if you're dealing with like very sensitive data. So I'm going to store this as alpha A. So I'm not sure if you guys know how to store stuff. Really simple. Just grab the number you want, hit the store button right above on, and pick any letter you want. To pick a letter, you have to hit alpha, which hopefully is intuitive, and in green, any letter you want. So this way it's going to store it as A. So if I ever like say alpha A, it's going to call that up. This will help me when I do the other problems to make an answer more accurate. So for part B, when will the population reach 425 million people? Okay. So I'll do this again. Now I know my k-value is 0.0113. I got to solve for time. So I got to divide both sides by 180.7. And 0.0113 t equals natural log of all that junk. And then t will be all that junk divided by 0.0013. 0113, sorry. Said O too many times. And let's go to my calculator. Natural log of 425. Crap. See you again. Okay, so I get that 0.855. And then divide by 0.0113. So I'm going to divide by alpha A. So it'll take about 75 years. 75.71 years will be my answer. Or if you add to 1960, what's that going to be? 2035 or 2036? Somewhere in that ballpark is when that will happen. If you want to be a little more accurate, you could say like in, like, I don't know, July 2035. So about 11 years from now. And actually just have my own curiosity. What's the US population right now? Okay, 333 million people. All right, interesting. According to 2022. Now, the reason why I want to be accurate here is that what if I did this number and divide by kind of a rough estimate of k, like 0.012 or 0.011? You see, it's going to give me answers a little bit off, right? That's why I want to be a little more accurate with my results. So that's why it's good to store, because otherwise you're going to be misled and think, oh, it won't have until 2037. Like, no, that's wrong. So you do want, there's a certain respect for accuracy here and precision. Sometimes I confuse those words. Anyway, let's keep moving. Half-life. For those who've taken science class or apes, hopefully you learned about this. Just basically the time it takes for half of substance to lose. Sorry. What was that?
Can you get us to like radiation?
Yeah, totally. Yeah. For half of for a substance to lose half of its original amount. So in this case, whatever. Oh yeah, she made this up. Okay. Yeah, that's funny. All right. Got me there. Anyway, the half-life is 98.6. Find the exponential decay model. Okay, so here's what we're gonna do, guys. I'll use this. A will stand for amount. Okay. So here's the deal. We need to solve for k. So this is t when what is true? When your amount equals half of what? Equals half the original amount. Let me put this as a text box, because I recall when I took some science classes and I wrote down the notes and I was like, wait, what does that mean? Like, you're trying to make sense of it. So I'm trying to put myself in your shoes, right? So what this means is that when A equals half times that means that the new amount is half of the original amount. We make this connection when dealing with half-life word problems. The initial amount. Right, so that's what that means, okay? So when a equals half times a0, so that's why I have to make that connection, because the t value assumes that, right? The t is assuming that, very important. So that means that half equals e k times 98.6. So 98.6 equals natural log of 1/2. Natural 1/2, I think, is negative 0.693. That's kind of a, oh, there's a k there, my bad. So,
Wait, what's 1/2 there?
what was that?
What's 1/2 there?
What do you mean what's 1/2? No, a divided by a sub 0. Sorry. What I just did is I divide both sides by a sub 0. Sorry if I glossed over that. Because again, we're told that, right? That a is half of a, or actually you could just do this. Replace a with half of a sub 0. So half equals EKT, if that helps. And if I solve for k, it will be natural log of 1/2 over 98.6. And what's that going to be? So natural 1/2, I think, is always negative 0.693. Yeah, divided by 98.6. And it should be negative because it's you're losing. It's the k. So it's negative 0.007. So I'm going to store that as alpha a. So negative 0.07. I know, terribly exciting stuff, right? Okay. So a equals a sub 0 times e negative 0.007t. That's your model for this particular element that this is to be made up. Then part B. Suppose on a particularly amazing day, 85 grams was emitted into the classroom. How long will it take for it to get down to 10? So 10 equals 85 times E negative 0.007t. So 10 divided by 85. Divided by alpha A. And there we go. And the times in, this is measuring what? We did this in hours. Okay, so this will be hours. So 304.424 hours. So hopefully that makes some sense how that works. We're okay with that? Yeah. And again, it's very important that you try to store that value. Because, I mean, if you look at alpha A again, I mean, it's pretty sensitive. You're going down to 3 decimal places. If I just divide by negative 0.07, will that change things a little bit? Let's see. Let me take this, but change that to negative 0.007. Yeah, it does change it a little bit, guys. It's 305.7. Like, so that does kind of make a difference, especially if you're dealing with like anything scientific where you need to be precise, right? So you will lose a point if you don't have the answer spot onto the decimal place. So be careful about that. If you want, you could just write out the whole decimal, like all those digits, but just store it. That'll be easier. And again, it's all being recorded, so you can watch this again if you need to see how to do it again. But it's really simple. Sit store in the letter, alpha, whatever letter you want. Right. Another type of model, logistic growth. We talked about this briefly early in this unit. Logistic models are actually more reliable because, yes, things will grow exponentially but after a certain time, things have to hit a limit, right? Like COVID. Like if you're looking at people getting affected with COVID on this campus or getting the flu, ultimately everyone gets sick, and that's it. It's not going to keep rising, right? Or if a certain community gets like infected with a disease, it just hits a carrying capacity, right? So that's why these models are a little better, or this model's a little better. When x equals 0, that's the initial value. There is going to be a point where it's increasing very quickly, and then the curve flattens out. When they talk about COVID, like the flattening of the curve, they're talking about this actually. That's actually what they're talking about. So this actually has a lot of relevance. And they use E as part of the model. It just makes it easier to work out. A and B are just constants, and C is the carrying limit. So we got to solve for these constants. Actually, fortunately, they give us a formula, so we don't have to solve for anything. Okay. That's nice because it could be a pain to solve these. So you got your model here. Apparently, 15,000 people is the population of the town. That's the carrying capacity. How many people became ill when it began? When it began, that's t equals 0. So that's easy. F of 0 equals 15,000 over 1 plus 15 times e to the 0 power. What's e to the 0 power? Good. So then what's going to be at the bottom then? 1 plus 15, right? Because 15 times 1 is 15, and you need 1 plus 15. Remember, only e is risen to the 0 power. Please do not, and Alex, can you put your phone away, please? Thanks. I can totally see you. Like, all right. Anyway, yeah, because the 15 is not part of that exponent, right? So let's use a calculator. 15,000 divided by 16. So, wow, 937.5 people. So we'll say roughly 938. We'll approximate it. Now, how many people were ill by the end of the 3rd week? And this is terms of weeks, right? Yeah. So you want F of 3. So you got to plug that in. 15,000 over 1 plus 15 times E, negative 1.4 times 3. That's easy, right? And let me go back to the calculator. Negative 4.2. So we'll say roughly 12,246 people were infected. We're good with that? Okay. Yeah, it's all good. Of course, 100%. Yeah, fully. Yeah, because I think it's hard to do this in a scientific calculator. So, I mean, I think what we'd actually, hold on a sec. Let me pause the recording. Let me check, because I have a copy of the test right now. Hold on. Okay. Yeah, because it would be much easier to do that in the calculator. And then finally, for this one, the carrying capacity is just the highest it's just the highest could be 15,000. Because what you're assuming that T is approaching infinity. If T gets really large, ultimately everyone's going to get sick, right? So that's what happens. Okay, last one. This formula is incredibly popular in calculus classes. It's a little confusing at first, so let me kind of walk you through it. Oh, I got to take attendance. Is everyone here? 5, 8? That's right. All right. Okay.
Here we go. How's the formula work? So T sub 0 is your initial temperature. Let's say you go to Starbucks, right? You go or eat wherever you go for coffee, right? So that'll be the temperature of the coffee. Think of it like that. Like maybe the coffee's at the boiling is 212 degrees Fahrenheit, maybe it's like 180 degrees Fahrenheit. I don't know, something really high, right? And by the way, whatever temperature you use doesn't really matter. It's up to you what temperature you want. Because you gotta make sure you use the same temperature units throughout the whole problem, right? I mean, other countries use Celsius, right? Here we use Fahrenheit. We're special. So the C is temperature in the room. Like what temperature do you say this room is? I mean, actually, what does it say?
70.
There we go. So we'll say 70 degrees, right? So what's going to happen is if I take your coffee and put it in this room, it's going to cool down eventually, right? Just because it's in an environment that's cool than coffee itself. So it'll take some time to cool, but how long it takes, it depends on the air pressure in the environment, depends on the material that's cooling down, like you're looking at water, maybe the insulation. There's all these, that's actually all like engineering stuff. It's kind of cool, but very complicated. I used to do that years ago, but not. So that K value is determined by all these other external factors, which we won't worry about, but we'll solve for K. And then this is the final temperature. Let's say you're not gonna drink your coffee until it's maybe a certain temperature, like doesn't use that right temperature, right? Maybe like 120, 130. I don't know what the good temperature, but we want to find that right temperature, right? So we're gonna try to figure out how this. And so, you know, spend some time. It's gonna take some time to get there, right? It's gonna take some time to cool to a certain temperature. So that's how that formula works.
It's a lot going on, but it's really not that bad. It's actually a really, pun intended, cool formula. Get it? All right. Stop. Okay, right. It's a neat formula. It's a neat formula. Okay. So we'll say a clay pot removed from a kiln with a no, dumb dad joke. Sorry. I know. 17 degrees Fahrenheit. Okay. It's placed on a table in a room where the temperature is 80. So the room is 80 degrees. Okay. So it's kind of hot. Kind of warm the room. And after an hour, it cools down to 1250. So we need to find a model. Okay. So 1250 is T. Because that's what it cools at, capital T, by the way. This is initial temperature. And that's C. Because C is the surrounding environment. So it's going to equal the surrounding environment plus 1700 minus 80 times E. And after 1 hour, okay. So what are you going to put for T then? For little t, sorry. After 1 hour. But they said minutes though. 60 exactly, right? And your job is to solve for K. Now, how this formula is devised, I think Sir Isaac Newton came up with this formula, and how he, I don't know, but it works. It has a lot of applications in calculus for sure. So that's 1170. Make sure you follow order of operations correctly, guys. Equals 1620 times E60K. Okay. I'll need a calculator to work this out. So let's do this in the calculator. We got to do ln of all that junk divided by 60. ln of all that junk. Yeah, it's kind of a small number. Negative 0.00542, I'll say. And again, you don't want to round it too soon because it's going to really throw our answers off a little bit. So alpha, store as alpha A.
We were gonna round it. How far back should we go? Like 6.
Honestly, I just do a crap load. I would do the whole thing.
Yeah,
I mean, 6 is usually safe. Just store it. I'm showing you how to do it. Let's do it. Okay. So now our formula is this, right? It's going to be T equals 80 plus 1620 times E negative 0.00542 little t. That formula will help us to determine how long it takes for a certain to reach a certain temperature for this clay pot that's being removed from a kiln. So now let's look at part B and C. What temperature is the pot after 3 hours? And how long will the temperature, how long until the temperature of the pot reaches 100 degrees Fahrenheit? Because 100 degrees Fahrenheit, then you could touch it, right? If not, you're going to burn your hands, right? That's bad. So let me get rid of all this other junk here. All this work I don't need anymore because I've already taken care of it. Okay, so after 3 hours, but what are you going to plug in for T? 180, right? Yeah, because remember it's in terms of minutes. And don't add that 8 to the 1620, guys. That's dissipating the order of operations. Please don't do that. You guys are well past making those mistakes. That would make me very angry. So, not very angry, but just not happy. So please don't do that. See here. 80 plus 1620 times E alpha A times 180. So it cools down to about 690 after that much time has passed. Okay, it makes sense because it was 11:20 before, or 11 something, or 12:54 for 1 hour. So 690. It's not linear, obviously. It's exponential. I think it's degrees Fahrenheit. Yeah. And by the way, if you were not terribly accurate with K, let's say you did negative 0.005. You see, it's gonna be off, right? That's a pretty big deal. You're off by 40. Like, that's not good. So when does it cool down 100 degrees Fahrenheit? So we're gonna say 100 equals 80 plus 1620 times E. So you subtract the 80 and simultaneously divide by 1620. I'm just combining some steps, guys. In the interest of time. So T will be the natural log of all that junk. Over So it takes about 810 minutes. Which is what, about divided by 60. So 13.5 hours. So if you pull this out, say like at 7 a.m., that means that probably around like 8:30 p.m., you can touch it. It's fine, right? 100 degrees, you can hold it. But if you're not very careful with your calculations, you're gonna probably go to the ER with some 3rd-degree burns. Because if I divide by negative 0.005, oh, let me sorry, it'd be 878. Actually, okay, you won't burn yourself because you'll just be waiting longer, I guess. But you get the point, is that like, or maybe you need this right away. I mean, it's just, you need to be accurate, right? So just make sure you're accurate with your calculations. Otherwise, you'll be off by quite a bit. Okay, I think that's about it. I think that covers everything. It's a very thorough lesson. Stop the recording.